In this video, we're going to take a look at section 2.5 on inverse functions. I'm looking to see if my glasses are going to have a glare from the light. It looks like it might, but I don't know, I feel like I'm having trouble seeing the screen. I don't know if it's age or just spending too much time in front of my computer, but I thought my glasses might help me stay a little more focused. All right, so let's talk about inverse functions. The inverse of the function f of x is the function g of x such that f composed with g of x equals x and g composed with f of x equals x. So we just talked about composition in the previous section 2.4, and we're using that concept immediately here in 2.5 to define this concept of an inverse function. So when you take the composition of two inverse functions, whichever way you might do it, whatever order you want to do the composition in, if they're inverses of each other, you will get x as a result for your equation. What's happening is effectively f and g cancel each other out. So we talked about this a little bit in section 2.4, that you can think of functions as machines that take an input, make some changes, and produce an output. Right? So g, when you have f composed with g of x, g will be the first function to get used. It will take the value of x, whatever it is, make some modifications to it, change it in some way, and produce an output of some kind. And then who knows what the output is. F will take that output as its input. That's how compositions work. And when f takes that output as its input, it reverses all the changes that g made and produces the original value that started the whole thing. And x is what comes out, the thing you started with. So g changes x, f changes it back to x. Right? And so they cancel each other out, and that's why they're inverses. So, in math, we use the word inverse to mean the reverse or to cancel out, right? An inverse is something that cancels out something else. And this is how functions cancel each other out. G makes changes to a number, f reverses those changes and gets you back to the original input, and vice versa. So if we go the other direction and let f go first, f will make some changes to x, produce an output. G will take that output, reverse all the changes, and get you back to the original input, which is x. So g essentially negates or undoes everything that f is doing. Now, getting the answer to be x, you might wonder, why, if it's canceling out, why is the answer x? To have two things cancel each other out it's a moving target. It depends what you're trying to get to cancel out. So I usually go through this exercise with my face-to-face classes. I'll say, what's the inverse of addition? And everybody knows the inverse of addition is subtraction. Right, so if I have x plus 5 equals something, and again, don't worry about the details of the equation, but if I want to do the inverse of this operation of adding 5, how do I invert that? I subtract 5. And of course, I would do that to the other side of the equation. The point I want to make with this exercise is, what is the net result when you do the inverse of addition? Plus 5 minus 5, the net result is 0. That's how you know you've accomplished the inverse of addition, when the outcome is 0. So that's our target when we're doing the inverse for addition. What about multiplication? Right? Let's say we have 3 times x equals something. What is the inverse of multiplying by 3? Dividing by 3. Of course, we do that to the other side as well. What is the net result here of dividing by 3? 3 divided by 3 is 1. So that's how you know you've accomplished the inverse of multiplication, when the outcome is 1. That's what you're expecting to get when you apply the inverse for multiplication. So for addition, the target is to get 0. For multiplication, the target is to get 1. For functions, the target is to get x. And the operation through which we get that result is composition. All right, so that's how it relates to the concept of an inverse. So there are essentially two kinds of inverse problems in section 2.5. The first one we're about to take a look at is, here's a function, find its inverse. This is the method by which we will do that. The second type of problem is, here's two functions, are they inverses of each other? To determine if two functions are inverses of each other, we will use the definition. All right, we'll use this to determine if two functions are inverses. We'll look at the composition of both of those functions in both directions and make sure they both equal x. And that's how we will confirm when two functions are inverses of each other. All right, if you're given one function and you're asked to find its inverse, you will use this method called the switch and solve method. Just before we get into that method, let's just talk about conceptually what an inverse function should look like. So let's pick an easy equation like f of x equals 2x plus 3. All right, so what does this function do when you plug a number into it? Let's list out the machinery, the components of this machine would be a better way to say that. All right, and we can actually identify that a little bit better, maybe by picking a number for x. So let's pick x equals 5, right? Now if I pick that number for x, what does f of x do with that number? It takes the number, so it takes 5, and then what's the first thing that's going to happen when we plug 5 into this equation? It's going to multiply it by 2, right? So if I take 5 and put that in the function, it's going to show up over here, and following the order of operation, the first thing that will happen is we're going to multiply it by 2. So we're going to multiply by 2, and we'll get 10, of course. And then we will add 3. Right, and then 10 plus 3 is going to give me 13. Right, so f of 5 is equal to 13. This is what f of x does. And this is why we use symbols in mathematics. So whenever I have a student make the comment that math made sense when it was just numbers, now it's like a foreign language, we have all these symbols, why can't we just keep it in words? You know, why do we have to use all these symbols and whatnot, and variables and all that stuff? Because if you didn't, this is what math would look like. It would look like this, and it would be even worse. It'd be more tedious, more difficult to understand, because you would have to like step by step explain what you're supposed to do, in these math problems if you're going to use words. All right, so this function would look like this if we had to like outline it step by step using words. And imagine taking something like this and having to like find the well, I guess we're about to find the inverse, but like doing other things with this function, graphing it, or solving it, setting it equal to something and solving it. It would be hard to do if this is the way it was presented, right? Working with this would be difficult. This is much easier to work with. So that's why we use symbols. It saves us from having to write out everything in words, and it makes it easier to manipulate. That's why math looks the way it does. All right, so we want to reverse this. We want to find the inverse. So how do I undo all the stuff that f just did? If I want to undo all of this, I have to start with the last thing that was done and reverse that. So the inverse here, the first step here is it will take the result from f, which was 13. So it's going to take 13. And then to reverse everything that happened, the last thing that happened was the adding by 3. So to reverse that, we will have to do what? We will have to subtract 3. And that gets us back to 10. And then to undo the multiplying by 2, we will divide by 2. All right. And so that's what the inverse function has to do to reverse all the stuff that just happened here. So see what happens, right? If you take 13, subtract 3, right? That's the first thing we're supposed to do. We get 10. And then divide by 2, we're back to 5 again. We're back to the number we started with. That's what should happen when you do the inverse. It should undo everything that just took place, get you back to the original number that you started with. This process does that. How do we write this as an equation? Well, we're taking a number. What's a good letter to use to represent that number? We're going to use x to represent that number. And what we're going to do with x is we will subtract 3, that's the next step, and then we're going to divide that by 2. And so this is what the inverse function looks like. Now we have special notation. Okay, let me try that again. We have special notation to indicate this is an inverse. So if we're calling this f of x, to indicate this is the inverse of f of x, we use an exponent of -1, which is just a label. It is not an actual exponent. It's just a label indicating this is an inverse function. So f inverse is the way you would read that. And this would be the inverse equation of this. Right? Whatever this is doing, this would undo it. And vice versa. Whatever this does to a number, this would undo all that stuff. All right. Now, that's just conceptually, dissecting a function and then reversing it. Reversing all of its functions, all of its operations, whatever you want to call it. And that's, it gives you an idea of what an inverse does, right? How it's supposed to behave, why it ticks the way it does, right? The switch and solve method will do all that for you, because while for this you might be able to analyze it directly, what's nice about this function is it does follow a very linear step-by-step process to get an answer, which is easy to reverse engineer. But other functions don't do that. So for example, we're going to see something like that. Well, let me just skip to it. We're going to see it later. Like this one, right? It does not follow a linear step-by-step progression. You pick a number for x, and it goes to 2 different places at the same time. And 2 different sets of things happen, and then we bring those results together and divide them at the end. But that's a pretty complicated process. And reversing something that kind of does simultaneous operations would be really difficult to do. So, thankfully, we have a process that kind of takes care of all that for us. It's called the switch and solve method. So the switch and solve method, following these steps, would get you this answer without you having to unpackage it the way that we did. Right? First step is to write f of x as a y. Let's just replace the function notation with the y variable, which is what it is, but just it's easier to work with if it's just y than having that clunky f of x, because we're going to be moving things around. Then we will switch x and y. Now, normally I don't recommend students memorize names for things. I mean, it's not a bad idea, but it's not really the thing I'm focused on. But this one, I really would recommend it because it's outlining, like, the name is the steps of the process. The name is the step. Yeah, I don't know. It sounds kind of weird. The name are the steps doesn't sound right either, so I don't know the best way to say that. But the name indicates what the steps are in the process. Say it like that. Rewrite f of x as y. That's not in the name. Switch x and y. That's the switch part of the switch and solve method. So this doesn't mean swap places. It means flip a switch. Everywhere there's a y, you flip the switch and it becomes an x. Everywhere there's an x, you flip the switch, it becomes a y. Every x becomes a y, every y becomes an x in step 2. Then you solve for y. And this is where all the work is. Solving it for y will force you to have to undo and reverse engineer that equation in order to get y by itself again. So when you're solving for y, you're undoing everything that's going on around y, and that's going to produce the inverse function of the original function when you do that. Then we rewrite y as f inverse. That's what we did here, right? It's just a label, right? We're just going to replace the y. Now that we're done doing all the work, we take y out, put the inverse notation in. And then the last step, I'll talk more about when it's relevant. But essentially, there's 4 steps here. Occasionally, you have to consider this 5th step, and I will let you know when that needs to be done. The Math Excel gives away when that's something you need to consider. So let's redo this problem here. We'll go down here. Sorry, if you hear some knocking, I think my daughter is hanging things on the wall. I don't know why she's doing that right now, and I probably should go check, but I guess I'll see what it looks like later. Okay, so let's go through the process with this equation. F of x equals 2x plus 3 with this function. Step 1, replace f of x with y. And I tell students, if you're in my class, I'm pretty generous on this problem on the test for partial credit. I'll give you a point for that. You really haven't done anything yet, but I'll give you a point. Usually I grade all my problems out of 5 points, so that's 1 out of 5 points. That's 20% of the credit for that problem. Step 2, switch x and y. Everywhere there's a y, it becomes an x. Everywhere there's an x, it becomes a y. All right, I'll give you another point for that. All right, so now you have 2 points out of 5 on my test. Step 3, solve for y. And this is where we're going to have to do the heavy lifting. Right? We're going to solve this for y, and this one's actually not too hard, but some of them are going to be pretty challenging. First step to get y by itself here is to do what? It's to subtract 3. Well, that should sound familiar. That's exactly what we did first up here, right? Once we had a value for x, the first thing we did is we subtracted 3. That's the first thing we're doing here. All right? And so we're going to subtract 3. Let me go back to my same color. Subtract 3. So we'll get x minus 3 equals 2y. Then, to get y by itself, we have to divide by 2 to reverse that multiplying by 2. So notice that by solving this for y, we are reversing the original function's operations, right? We're subtracting 3 to undo the plus 3. We're dividing by 2 to undo the multiplying by 2. And we end up with, need a little more room here, we end up with x minus 3 over 2 equals y. So that is step 3. Sorry, sometimes my computer gets a little noisy too. Sorry about all the little noises. If you can, I don't know if the mic's picking them up or not, but sorry if you can hear those. Okay, step 4, a pretty easy thing. Replace the y with the inverse notation. So the function notation. So we're going to call it f inverse, and that's it. The right-hand side, well, what was the left-hand side, notice I'm flipping it around the other way, but the other side of the equation is not going to change. And that's it. And step 5 does not apply to this problem, so don't worry about it. That's the answer. There's nothing else to consider. And it's the same answer that we got previously, right? So we can confirm that method is producing reasonable results with this example. So why don't you try this problem? So go ahead and pause the video. I'll do the same. Find the inverse of this function. It's a little unfortunate that, again, to get these problems off of Math Excel, I go to your homework assignment on Math Excel, I preview it, I generate an example of it, and I just kind of snap pictures of various problems that I want to talk about. So I don't really get to choose the numbers that are here, and it's unfortunate that they're both 3s, so I apologize for that. Because then, like when you see the answer, you don't know which 3 went where, Whereas like with this problem, you can kind of see what went where, right? The 2 went on the bottom, the 3 went here. It's kind of interesting to be able to see that. You won't be able to tell with this one. Anyways, pause the video, find the inverse, and then resume the video to see if you came up with the correct answer. Okay, so here's the answer that you should have arrived at. Using the switch and solve method, replace f of x with y, switch x and y, and then solve for y. So that's, step 2 is switch, step 3 solve. Again, same steps as the last problem that we just looked at. And then you get this result, and then you replace the y with the inverse notation, and that's the answer you should have got. All right, now in the directions, it indicates f of x is a one-to-one function. I used to actually spend quite a bit of time talking about that concept. But it's not really relevant to the rest of the chapter or the rest of the course. It's interesting, but I also found, and maybe it's my fault because like what I'm doing now, I maybe over-explain some problems and get a little bit off track in other areas. But I have trouble covering all the material that I need to cover in a semester. It's a tight fit, and so I was looking for little topics I could just cut out here and there to make it easier to cover all the material that needs to be covered. And one-to-one, I went ahead and let that go. Just to give you a quick explanation, a one-to-one function, a function has the property that when you choose a value for x, there is only one corresponding value for y. One-to-one is just the reverse of that. So it's not really all that complicated. For each value of y, there can only be one possible corresponding value for x. And I didn't mention it in the definition, but for a function to have an inverse, it has to be one-to-one. It has to have that property. If a function is not one-to-one, then it can't have an inverse function. It can have maybe an inverse equation, but the equation wouldn't be a function. And so for a function to have an inverse function, the function has to be one-to-one. And like I said, that means for every value of y, there's one corresponding value for x. You can check for one-to-oneness by doing the horizontal line test. So basically you do the same test you did for functions, but you just flip x and y around, just like we're doing in this equation, right? Switch x and y. And so instead of vertical line tests, which is what you do for functions, you do horizontal line tests to tell if it's one-to-one. For tables, to tell if it's a function, you look for repeating values of x. To tell if it's one-to-one, you look for repeating values of y. So it's the same rules, but just where x and y are switched. All right, so let's take a look at this one. So let's find the inverse of this function. We'll start by step 1. Y equals 2 plus square root of x minus 3. That's the first step. Replace the function notation with y. Step 2, switch x and y. So everywhere there's a y, it becomes an x. Everywhere there's an x, it becomes a y. Step 3, we're going to solve this for y now. The first step here would be to get rid of the 2, which is being added to the square root. So to cancel it out, we need to subtract it. So we get x minus 2 on the left-hand side equals square root of y minus 3. We talked about back in chapter 1 solving square root equations. So as I mentioned at some point in one video, and as I mentioned in all my face-to-face classes, you can't just learn and then forget the material for a test. So I think a lot of students, and that might have worked for a long time, but it's going to become less and less an option as you take more and more challenging classes that build on previous knowledge, because what makes a class more challenging is that it's building on previous knowledge. And that's how you get to like really, rigorous, top level results. And that's how you get theories and see how things connect, is you have to be able to build on what you've learned previously in order to reach that next level, And so you can't just say, I got to learn this for this test, do okay on the test, or do good on the test for that matter, and then just forget everything that you just learned when you move on to the next chapter. That's not going to work very well in this class. And I think, like I said, as you take more and more challenging college classes, that approach is going to work less and less well. So you need to adjust, learn in such a way that it sticks, right? And my opinion, the best way to get it to stick is to try to understand it. Don't just try to memorize how to get the answer, because I'll tell you, like on this problem, I like to put this problem on my test. And Math Excel puts this formatting here, and maybe I'm a little bit too lazy, but I just print the test off of Math Excel. And so this will be on your test. And students will memorize that, well, this number just ends up here in this box, and this number ends up in this box. But if you're my student, I am not going to give you credit if that's all you do. So if you don't have work supporting that answer, you won't get any points for this problem, even if that's the right answer. And you're approaching learning in the wrong way if to you learning is just memorizing enough to get the right answer on enough problems on the test to pass the test. You want to understand. And if you understand the material, because your memory will let you down. You're going to forget things. If the way you're learning things is to remember or memorize, that's not going to stick, right? Not everything will anyways. But if you understand it, which is how I try to teach. I try to teach for understanding. That doesn't leave you, right? When you understand something, you understand it. And it's there a month later, a couple weeks later. Because like I said, I find a lot of students in my classes, we cover a topic, and then 3 weeks later, we revisit it for another problem. We come back to that topic because we need that knowledge to be able to do a new problem. And half of my class is forgotten or more. Right? If you can't hold on to it for 3 weeks, you didn't really learn it to begin with, right? You just maybe memorized enough to get through that patch of time, but you didn't really understand it. Because if you understood it, it would still make sense 3 weeks later. So try to approach learning with the intent of trying to understand why things are done the way they're done, and not just how do I get the right answer, but why is that the right answer? And so that's, I'm sorry, I went off track there, but it's really an important, because I can remember as a undergraduate student, I was taking electromagnetism. And I didn't do very good in that class. I wanted to do physics, and I was not good at physics, unfortunately. I really liked that subject. I always had a knack for math, but I just could not seem to get a knack for physics. So, but that teacher really, and he looked like Luke Skywalker, honestly. I remember him looking like Mark Hamill. It was weird. But he on those tests, we were allowed to have like crib sheets, like a, cheat sheet, if you will. But it was, it was allowed, so we could put notes on there. And what I always did was I took all the homework problems, wrote them as small as I could, and fit as many on this piece of paper as I possibly could. And I did bad on the test. And I think he was aware that some students were approaching it that way. And he said, like, if you feel you have to write down a bunch of examples from a lot of problems, on your cheat sheet, you're not going to do good on the test. It doesn't matter how many problems you write down, because, every problem is going to be a little bit different, and you're not going to find one that exactly matches. What you need to do is understand the material, and then you won't need to write down as much. So he could almost predict who was going to do good on the test and who wasn't, because the people that filled up their sheets weren't going to do well, because the reason they're filling up their sheets is because they didn't understand the material. And if you understood the material, you didn't need that much on your sheet. And so, he explained it to me, and it stuck with me all these years. But it took me a while to really understand what he meant. It didn't make sense to me. I was like, I'm still just going to write down all these examples, and maybe that's why I never got good at physics. But and you'll have teachers throughout your, academic career. I don't know, however you want to call it. That will maybe make that point here and there, because he wasn't the only one that made that point to me. But, and it might not make sense at the time, but eventually it sinks in. And so hopefully, I don't know if you're hearing it from me for the first time, but hopefully you'll have some other teachers kind of tell you the same thing. And, eventually it'll make sense to you once you reach a certain point of maturity, or once you've had enough experience, you start to realize, or especially if you ever become a teacher, because once you see it from the teacher's perspective, you know exactly what they're talking about when you're trying to teach other people. So anyways, let's get back to this problem. So we want to solve this for y. So now I'm remembering, how did I even get on that topic? Back in chapter 1, we talked about solving square root equations, right? We went over these problems. So hopefully you remember from chapter 1, even though this problem has two variables, it's still the same principle trying to solve this for y. We got to get rid of this square root. How do we do that? We raise it to the second power. If we do that to the right-hand side, we have to do that to the left-hand side. And remember, the rule was it's all or nothing. You have to raise the entire left-hand side to the second power. Right? Not x squared and 2 squared, but x minus 2 altogether has to get squared. All right. So then what are we going to get? We're going to get x minus 2 squared equals, here the power of 2 cancels out the square root. We get y minus 3 by itself. And now we can solve this for y by adding 3 to the other side. And so we get x minus 2 squared plus 3 equals y. And then step 4, replace the y with function notation. So f inverse. I'm just going to flip these around the other way as well. So we get x minus 2 squared plus 3. And that is the answer. That is the inverse function. And I can see why Math Excel formatted. I don't like it. I think it just gives way too much away about, what the answer is supposed to be. And especially because they wrote the square root equation in this weird order, it just stands out so bad. The numbers just kind of stay in the same order when you type it into the way they have it formatted. But the reason they did that is because they're trying to indicate to you to not FOIL this out. They're saying just leave it as x minus 2 squared. Right? And that's why they have it set up like that. Otherwise, you wouldn't know, and you think, I have to FOIL this because that's what we have to do on every other problem, right? But for some reason on this problem, they don't want you to do that. And so that's your function. Now, that's your inverse function. There's this extra box they want you to type something into, and this is asking for what x is allowed to equal. So it doesn't say it, doesn't call it by its name, but what it's really asking for there is the domain. So here, step 5 is relevant, and this is how you will know step 5 needs to be considered. If they ask you for the domain for the inverse function, that means step 5 needs to be activated, right? So let's go back and look at step 5. I somehow skipped it. Oh, I didn't skip it. It was just out of view. Step 5 right here. Okay. So, step 5, double check that the domain and range of f of x switch places for the inverse. So in step 2, we are switching x and y. But that means every characteristic associated with x and y should also be switching places. And 90% of the time, it automatically does that without us having to even worry about it, right? So when we switch x and y, remember x is, sorry, I'm saying the wrong thing. The domain is what x is allowed to equal. The range is what y is allowed to equal. I don't know what's wrong with me. When we switch x and y, the domain and range should also be switching. Now for this function, it automatically did. We didn't have to worry about it. When we switched x and y, the domain and range automatically switched places. We didn't have to take any action on that. But on problems where they are asking you for the domain, the reason they're asking you is because it didn't automatically happen like it was supposed to. So you have to step in and force it to happen. You have to force the domain and range to be what they need to be for them to be inverses, since they didn't automatically become the thing they were supposed to become. So let's go back to this problem and consider what is the domain and range of the original function. And then let's make sure that they switch places for the inverse function. All right, so what is the domain and range of the original function, f of x? The domain, the range. Now, this is another topic that we've covered previously in this chapter. Now, I think the problem that students have when I'm teaching this in class is they haven't done the homework yet for that section, even though it was 2 sections ago. But we talked about in section 2.3 how to graph square root functions, which is what this is, and that will be the easiest way to determine the domain and range of this function by looking at the graph. And so if you haven't done your homework for section 2.3, then this part of the problem is going to seem really hard because you haven't learned what you need to learn yet to make this part easier, right? So the square root function, remember, looks like this. You're supposed to have it memorized. It's the half a sideways parabola. We also saw it in 2.4 briefly. But this time, it doesn't stay there. We're subtracting 3 from the x. We're adding 2. How does that change the graph? That's going to shift it to the right 3 and up 2. And if that doesn't make sense, if you're not sure why that's happening, go back and watch the video on section 2.3 and practice those problems. Do the homework for section 2.3. Then this should make sense because this is actually, relative to those problems in 2.3, this is one of the easier ones that you might have to deal with, one that's like that. Now, what is kind of weird is they have the plus 2 in front of it instead of after it, so that's why it's not stretching or shrinking, because it's not being multiplied to the square root, it's being added, and so that's going to shift it up or down. In this case, up. Right, so I'm going to take this graph, shift it to the right 3, and up 2. The rest of the graph just tags along with it. And that's it. That's all. I don't have to make it look good. I don't have to plot points. I don't have to draw it any better than that. That's perfect for finding the domain and range. All right, so remember, the domain is how far to the left, how far to the right the graph goes. So what's the furthest to the left? It's 3. How far to the right? Infinity. The range is how far down, how far up. How far down does it go? 2. How far up? Infinity. So that's the domain and range of my original function. The inverse function should have those flip around. Let me do this. Okay, I want to keep everything in the screen there. So what should it become? The domain here should become the range. So let me actually draw arrows. So the domain and range should switch places for the inverse function. Oops, I don't know what I'm writing there. All right. And so the range of the original function was 2 to infinity. the domain should now be 2 to infinity for the inverse. And then, how do I want to say this? The domain of the original function should become the range of my inverse function. So my range should become 3 to infinity. All right. So drawing arrows here, these should have switched places. The domain should become the range of the inverse. The range should become the domain of the inverse. Now, what is the domain and range of our inverse function? So if we look at the function without considering what it should have become, if we just consider this, we also learned how to graph these in 2.3. It's a parabola, right? This is a square function, which looks like this. I'm not going to get there. All right, it's going to look like this. And we're going to shift the graph right 2 and up 3. So if I do that with this graph, to the right 2, up 3, looks like this. Now, without making any modifications, what is the domain and range of the graph that you see here? The domain would be how far to the left? Negative infinity. How far to the right? Positive infinity. The range, how far down? 3. How far up? Infinity. Right? And so the function I get has this domain and range. It should have become this domain and range over here. So notice the range actually is fine. It matches up. It became what it was supposed to become. But the domain didn't. We needed the domain to be 2 to infinity, but for this function, the domain by default would be negative infinity to infinity. So what we have to do is step in and override the domain. We have to, what I think the technical mathematical term for it is restrict the domain. The domain would have been negative infinity to infinity. We are going to restrict the domain to just 2 to infinity to get the domain we're supposed to get for this to be the inverse function. So I'm overriding this one and I'm stating it needs to be this instead. I'm stepping in and manually changing it. I don't know how else to say it. By doing that, what happens to my graph? Because notice I talked about it a moment ago, one-to-one functions. This is not a one-to-one function because it doesn't pass the horizontal line test. And if it's not one-to-one, it can't have an inverse and it can't be an inverse. By restricting the domain to just 2 to infinity, what part of the graph will be left? This part goes away. Because here's where 2 is. So if I just restrict the graph from 2 to infinity on the x-axis, I just get this part of the parabola, which is now one-to-one because now this horizontal line only crosses the graph once instead of twice. So that's why we need to step in and modify the domain for this function to serve as the inverse of the original function. If we leave it unmodified, it's not an inverse because it doesn't match the graph appropriately. It's not a one-to-one function. There's issues with it. So I need the domain to be 2 to infinity. Now, MathExcel didn't ask for the answer in interval notation. On the test, I would be perfectly happy to accept this as your answer. You don't have to write it a different way. But on the homework, you have to type it into MathExcel. And so they have this, and they have a box here. And so we want x to be greater than or equal to 2. Right? 2 to infinity means x has to be bigger than or equal to 2. And so that's what you would type into the box there. Okay. So that took a while to talk about, but you only have to worry about that domain and range switch if they actually ask you about the domain. If they don't ask you what is the domain for the inverse, what does x have to be, then you can just assume they automatically traded places and nothing has to be handled manually. Okay. One more example of finding the inverse given a function. So let's go ahead and take a look at this one. We'll go through the steps. You might say, I do like to alternate where possible. I do one, maybe have you guys try one. It's what I do in my face-to-face classes. But this equation's a bit different from the ones we did previously and a lot more challenging. So I'm going to go ahead and do this one for you. Step 1, it's the same steps though. Replace f of x with y. So we get that. Same equation, just y now instead of f of x. Step 2, switch x and y. Now I'm doing like this, but that's really bad form for me because you're not swapping places, you're flipping a switch. And so everywhere there's a y, flip the switch, it becomes an x. And then everywhere there's an x, you flip the switch and it becomes a y. So both of these x's become y's. So again, if you're my student on the test, you make it this far, 2 points. That's an easy 2 points out of 5 that you can get on the test. But if you want the rest of those points, you're going to have to, I wanted to say buckle up, but I feel like that's being a little too dramatic. But yeah, it's going to be a rough ride from this point on. So 3, solve for y. It's going to be tough to do, right? We have a fraction for one thing, so got to think back to what we learned back in chapter 1. How do we deal with equations that are fractions? To get rid of the fraction, we multiply the common denominator to both sides. What is the common denominator here? It's 4y plus 2. So I have to multiply 4y plus 2 to the right-hand side, 4y plus 2 to the left-hand side. I'll use parentheses there. So we get 4y plus 2 times x on the left-hand side equals 3y plus 3 on the right-hand side, because what happens here is the 4y plus 2's cancel out, and we're just left with the 3y plus 3. And on the left-hand side, what you see here is what you get. Right? It's this. Now, the second obstacle, so the first obstacle was fraction, but we handled that. We've learned how to deal with that previously. Second obstacle is parentheses, right? I can't solve for y while there's 1 stuck in the parentheses. So even though you don't want them to mix, you don't have a choice. You have to distribute the x into the parentheses. And so you're going to get 4xy plus 2x equals 3y plus 3. Right. Now, the final obstacle, well, there's maybe 2 more obstacles here. You can't solve for y while they're on opposite sides of the equation, right? So we have to get all of our y's together on the same side of the equation. So I'm going to subtract the 3y over to the left-hand side. So now my y's will be together. And I don't want the x over here because there's no y with this term. So this one doesn't belong with this group. So I'm going to subtract the 2x over to the right-hand side. So get all of your y's on one side. Everything that doesn't have a y goes on the other side. And then we're going to get 4xy minus 3y, that's what we get over here, equals 3 minus 2x. Right, because these canceled and these canceled. Right. And then the final thing that gets in your way is you have 2 y's here. You can only solve for y, though, if there's 1 y in the equation. And unfortunately, these are not like terms. You cannot combine them together because there's an x in this term and there's not one in this term. So they don't just combine together very easily. So what we're going to do to manage that situation is factor out the common factor, right? There's a y in the first term. There's a y in the second term. It's a common factor. We can factor it out. So we're going to factor out the y. That's going to leave me with 4x minus 3 in parentheses. And now I can get y by itself by dividing the 4x minus 3 to the other side. All right. So we get y equals, we get 3 minus 2x on top, 4x minus 3 on the bottom. And then step 4 is to replace the y with function notation, inverse notation. So we get f inverse equals 3 minus 2x over 4x minus 3. Okay, so it's kind of, I wrote it a little bit sloppy, but I think I'm just going to leave it. I don't know, maybe I should undo that last part there, but I just feel like the parentheses are kind of hard to follow. Okay, sorry, I just can't let it go. I gotta fix this. This is just too sloppy. I don't know why I think that is, but I'm sure other things I've written are pretty bad too, but I just felt like that was a little bit too unreadable. Okay. And you don't have to do step 5 in this case because they're not asking for the domain, which means that must have worked out fine. And in fact, we haven't talked about how to find the domain and range for these kind of functions. We will see that in chapter 3. So it'll be a while, but we will get to it eventually. All right. So I have just, oh man, a few more actually, more than I expected. So I have a few more problems to look at. This one, it's the other variety. So remember near the beginning of the video, I said there's 2 different kinds of inverse problems. One where you're given the function and you're asked to find the inverse. That's what we've been doing so far. Now we're switching to the other type, which is, here's two functions. Are they inverses of each other? And I can remember when I first started teaching, and I put this problem on the tests, and my intention was for the students to find out if they were inverses by composition, by using the definition that we talked about way back here, right? Yeah, right here. Right. So here's how you know if two functions are inverses. You take the composition. If you get the answer of x either way, then they are inverses of each other. And I guess maybe I'm just kind of jealous because I didn't think of this, but what I had students doing on the test was taking one of the functions, doing switch and solve to see if it matched the other one. And if they matched, then yes, they're inverses. If they didn't match, then they weren't inverses. And that's a really genius way to approach it, really. Because the switch and solve method is pretty straightforward. It's an easy process, maybe not easy, but it's a good process to apply. It makes more sense maybe than composition does. And so it's a good idea, but definitely not the way I intended for the problem to be done. And I guess Math Excel became aware of that cheat as well, because on Math Excel, they don't just say, are these inverses of each other? It makes you find the composition. And then it asks you if they're inverses. So that's a way to get around that cheat is, I'm not just asking you if they're inverses, I'm saying you have to find the composition of these two functions first, and then based on that result, tell me if they're inverses or not. And so they're not using the composition notation, but that's what this is, right? This is F composed with G. This one's G composed with F. And they're asking us to find that first. So let's go ahead and do that. I'll do one, and then I'll pause the video and have you do the other one. So I'll do part A, have you guys do part B. So let's find F composed with G of X. That's going to be F of G of X. So remember, and then this goes back to just the last section, which again, the biggest issue when I'm teaching this material is that students have not worked on the homework yet for the previous section. And again, so if you're watching the video, if you're not in my class, you might be wondering why. If I already covered it, why haven't people done the homework yet? And maybe I need to change my policy on this, but I have the policy of having the homework be due when the test is done. So whenever we take the test, that's the day that the homework is due for the whole chapter. And so students will just kind of let it pile up. They don't keep up with the homework on a daily basis. They kind of wait to 3 or 4 days before the test and then just try to get it all done at once. And I know that's a really bad way for them to be doing it, but I think the students really do enjoy the flexibility of kind of being able to work on it as their schedule allows up until the day that it's due. Anyways, maybe I need to stop doing that so that when I'm teaching this, hopefully everybody's already taken a look at this material and knows what to do here. So what we need to do is substitute. Replace G of X with what it's equal to. It's equal to 3 over X plus 7. So I'm going to replace G of X with 3 over X plus 7. That is what I want to plug into F of X. So essentially what's happening here is we're taking G and we're plugging it into F. This is what G is equal to. That's what has to get plugged into F for X, right? So in place of X, we're plugging this in. And again, I talked about the confusion there in 2.4. So if that sounds confusing, maybe go and watch the video for section 2.4 again. Work on some of the homework for 2.4 before you try to attempt this problem. What we end up getting, and this one is especially confusing because there's fractions inside of fractions. So F of X is 3 over X minus 7. That's what the function is. I'm replacing this X with the thing I've circled in green here, but everything else is going to stay the same. So I'll still have 3 on top. I'll still have the minus 7 on the bottom, but in place of this dummy variable X, that's just a placeholder, I'm putting the actual live variable, which is 3 over X plus 7. Right. So let me, maybe I should use a different color to make it stand out so you can really see the substitution there. We'll have 3 over X plus 7. Right, so this is where X was. In place of that, we now have 3 over X plus 7 because that's what G of X is equal to. That's what we're plugging in for X right here. And so it's a mess. And we need to simplify it. So what's going to happen is the 7s are going to cancel out. Plus 7 minus 7, gone. So we get 3 over x. Now, what I tell my students when I'm grading, I get really picky about this because this is on the homework. I'm doing this in class, and it's on the practice test. And what I find students do, especially because it's on the practice test, they know it's going to be on the actual test, and they'll just memorize that the answer for this will be x, right? When the problem looks like this, the answer is actually just going to equal x. And so they know the answer they're supposed to get, but they're not sure how to get there. So when they reach this point, they kind of just cross everything out. But what I point out is that not everything here cancels out all at once. These 3s cannot cancel out while the 7s are still there. The 7s are blocking that from happening. So really, this is happening one step at a time. The 7s cancel out first, and once the 7s are out of the way, then we can cancel out the 3s, which I'm still skeptical if all students really understand how that's working here. So the way I think of it is division. This is 3 divided by 3 over x. And if I write it out like this is 3 divided by 3 over x. Dividing by a fraction can be done by multiplying by the reciprocal. And once you multiply by the reciprocal, you see the 3s are going to cancel out, and you get x. There are other ways to manage simplifying that, but that's the way I think of. But it doesn't just automatically happen. And it has to be done one at a time, really, to be done properly. So when I see students on the test that cross out the 7s, cross out the 3s, and just say, oh, the answer is x, I don't know. I'm pretty skeptical that they really understood how to accomplish that. All right. So what I would like you to do is pause the video and find the other composition, because this isn't enough. It's not enough for just one of them to equal x. We have to check and make sure both of them equal x. Now, 90% of the time, 95% of the time, if one is equal to x, the other one's going to equal x also. But there are exceptions to that. And in fact, I have an example of that here that we're going to see on the next screen. Anyways, pause the video, find g of f of x, and then resume the video to see if you came up with the right answer, and make sure you show your work. Make sure you're doing the work correctly as well. Okay. So the result you should have ultimately gotten was x. So you get x for both part A and part B on this particular problem. But the work getting there is not so simple. At least I don't think it's simple. Just to kind of point out a couple of mistakes I will see on the test. Again, this is not just my paranoia of me worrying about students making this mistake. I see students make this mistake all the time. And that is, they will put the plus 7 instead of being to the side of the fraction. So notice well, you can't really see it, but I'm copying down this function here, right? Because we're taking f. So what's happening in this case is we're taking f and we're plugging that in to g. So where this x is located, we're plugging this expression in there. Everything else is going to stay the same though. The 3 will stay the same. The plus 7, notice, is to the side of the whole thing. And it should stay there. And then the x here gets replaced with 3 over x minus 7, which I wrote in a different color to make it easier to read. So a common thing I will see students write on the test as they're writing it out is they'll put the plus 7 down here instead of being to the side. And if you put it there, of course, that's the wrong place for it. But also, things don't cancel out like they need to if the 7's actually down there in the denominator. So be careful not to make that mistake. So it should look like this. And then the other mistake, and like this one, it's hard to tell. It's hard to tell if a student really understands it or not because I can understand crossing out the 7's, and then yes, the 3's are going to cancel out after that. But here, I have to draw the line. If you're just crossing everything out at once like this, because the 7's are nowhere near crossing each other out. This one's stuck way down at the bottom. It's not at all apparent that the 7's will cancel each other out. And they, in fact, don't cancel each other out yet. What cancels out first is the 3's, right? Which you'll see as you work through the problem. So you take this fraction, think of it as division, multiply by the reciprocal. The 3's are the things that cancel out first. Once the 3's are out of the picture, then the 7's end up side by side and canceling each other out. But again, it has to really happen one at a time. It doesn't just all magically cancel out. All right, now we have x here, we have x here, so are these inverses? Yes. Inverses. I'm just going to put, it's not a complete sentence, but I'm hoping that gets the point across. All right. Because they're both equal to x, they are inverses. If they equaled anything different, they would not be inverses. All right. Let's take a look at this example real quick. And then I have maybe one more. It's about graphing. And I have a couple, but these are pretty quick because the graphs are already done for us. So we're pretty close to being done. Again, maybe we'll be done about around an hour, hour and 5 minutes or so through this video. So I'm sorry. Sorry for the run time. I really would like to try to have the videos to less than 50 minutes, but it's the same issue I encounter when I'm teaching face-to-face in class. You got 50 minutes in class, and I don't always get through all the material in 50 minutes. So I'll have some spillover that I address at the beginning of the next section, and it just kind of makes a mess of things sometimes. But so same thing. Find the compositions and then determine if they are inverses of each other based on that. So we'll do f composed with g. This is going to be f of, so we're taking g of x and replacing that with what g of x is equal to, which is square root of x minus 10. All right. And that means I want to take the square root of x minus 10 from g, that's what g is equal to, and plug that in as the input for f of x. So this x here in f of x will get replaced with this square root of x minus 10 from g of x. That's what this is asking me to do. And so we're going to have, in place of x, we're going to have this square root of x minus 10. And then that's going to get squared. And then we're going to add 10 to that. All right. The square root and the power of 2 cancel each other out. And we get x minus 10 plus 10, which means the 10's then cancel out. So it's the same thing here, right? The 10's don't cancel each other out initially because they're 2 cut off from each other. But once the square root and the power of 2 go away, the 10's find themselves next to each other side by side. Then they can be canceled out, but not before, right? They don't really cancel out here. And so we end up getting x, which is a really good sign that these might be inverses of each other until you check the other one. Right, so let's check the other one. We have g composed with f of x. That's going to be g of x squared plus 10. All right, so what's happening here is I'm taking what f of x is equal to and plugging that in to g of x. So this x here is going to get replaced by x squared plus 10. Right, and maybe I should switch colors here so they don't blend together too much. So we're going to get well, that was weird. That's a pretty cool shape. I could never draw that if I wanted to on purpose. I felt bad erasing it. That looked pretty cool. All right. So there's a square root. And in place of this x here, we're going to have x squared plus 10. Right. So that replaced this x, but then there's still a minus 10 after that we have to copy down. Right. So this is where x was located, and now we have x squared plus 10 in its place. But everything else stayed the same. What happens in this case are the 10's canceling out, and we get the square root of x squared, and it appears you're on the same path as the previous one. The square root and the power of 2 cancel out, and it would appear that you're just going to get x as your answer, but that is not the case. So I think, I don't know, I talk about it in all my classes at some point. I want to say I talked about it at some point in one of my college algebra videos. But the square root of x squared, I think I did when I talked about quadratic equations, doesn't just equal x. It equals the absolute value of x. The reason that has to be the case, just really quickly again, is if I choose a negative number for x. If I choose like -1, let's say, that was a really horrible -1. If I choose -1 and I plug that in here, if these are truly equivalent to each other, they should give me the same result. But they don't, right? Because if I plug in -1 here, when I square it, it comes out +1. And then the square root of 1 is just equal to 1. So if I plug in -1 here, I get 1. If I plug it in over here, I get -1. So they're actually not equal to each other for negative numbers, right? But we can fix that by putting an absolute value on it. And that way, when I plug in -1 here, the absolute value of -1 will be +1. And now they match each other. They already matched each other for positive numbers, but they didn't match for negative numbers. But we can fix that by using absolute value, and now they match for all numbers. So this is truly equivalent to this with the absolute value for all numbers x. Right, so this is actually the correct answer here. Now, that means they're not inverses though, right? Because if it doesn't exactly equal x for both of these, they're not inverses. So these are not inverses of each other. And the issue actually comes back to that one-to-one property. X squared plus 10, that's a parabola, right? We know what that graph looks like. It looks like this, right? The plus 10 shifts it up 10. It's not a one-to-one function, right? Horizontal lines cross the graph more than once. If it's not one-to-one, it can't be an inverse. Now, if we restricted it to just, if we restricted the domain to just 0 to infinity, that would just mean this part of the graph right here, then it does become one-to-one. How does that fix this situation? Well, if the domain is 0 to infinity, then you don't have negative numbers for x, which means you don't need absolute value, because the absolute value only has an effect. It only actually changes anything when you're plugging in negative numbers. If I know I'm not going to have any negative numbers here, then this becomes true. X squared of x squared does just equal x if all we're going to use is positive numbers. I wouldn't need absolute value for the case where we're only using positive numbers. And so then they would both equal x in that case, but only if you restricted the domain to 0 to infinity, which they didn't do here. And so given the function as it is, this is the result you get, and they are not inverses of each other. But that's the reason why. And that's how you could fix it. So there is a way to fix this. It's to restrict the domain, but we're not being asked to fix it, so we're just going to leave it as not inverses. All right, so the last topic here is graphing involving inverse functions. So notice the theme of this section is switching x and y. That's how you find an inverse. You switch x and y using the switch and solve method. The domain and range switch places. That's switching x and y for one-to-one. I said I wasn't going to teach it, but I practically did. It's the how do you say, counterpart to functions. And it's the same definition as a function, but with x and y switched. And so everything in this section is about switching x and y. The graphs will be no different. So the graph of the inverse function, f inverse, is the reflection about the line y equals x. So remember, reflection means you're flipping the graph over, but you're not flipping it over the x-axis. So again, if we go back to our discussion in section 2.3, we talked about reflections, and this is the only one we did in 2.3, reflecting about the x-axis. What we're doing with inverse functions is reflecting about a diagonal line like this. Right, so you can kind of see, should go like this and then flip to this, right? I'm holding it right. So that's how you find the graph of an inverse. You take the diagonal line where y is equal to x and rotate the graph about that diagonal line 180 degrees, and what you get will be the inverse, right? And so if you think about, I don't know where I want to draw this at, but so here we have the y-axis, we have the x-axis. Here's the line where y is equal to x. Now, if I rotate the graph along this diagonal line, think about what happens. The x-axis, when I rotate it about this diagonal line, becomes the y-axis. And the y-axis becomes the x-axis, thereby switching x and y. So by rotating the graph along this diagonal line, you're essentially doing the switch and solve method. You're switching the x-coordinates with the y-coordinates. You're switching the x-axis with the y-axis. And that's how you're getting the inverse, just like we were doing earlier with the equations. So for this problem, they're giving you multiple choices, and they're asking which of these indicates two graphs that are inverses of each other. So there's two graphs in every option, but only one of them has two graphs that are actually inverses of each other. So let me zoom in a little bit, because I know those graphs are kind of hard to see, and they kind of get fuzzy when I zoom in a little too much. But so which of these graphs show us, which of these answers show us two graphs that are inverses of each other. That's a good way to say it. And I'll usually ask my students to raise their hand, or I'll just wait for a student to respond, A, B, C, or D, and then I'll discuss. And it's okay to give wrong answers. I just want responses. Even if they're not correct answers, it still gives me something to talk about. We can still learn from it, and you shouldn't feel bad about giving an answer. If you're participating in class, you're paying attention, that's great. Those are all positive things, right? So let's say you think the answer is C. So the way you would check this is you would think about what the line where y is equal to x goes through the graph, and take one of the graphs. So one of them is blue, a solid blue. The other graph is a dash red, which I shouldn't have done this one dash red either, but the other graph is dash red. So what should happen if they're inverses of each other is if I draw this diagonal line where y is equal to x, and I rotate one of the graphs around that line, it should match up to the other graph. So if I do that with the blue graph here, if I take this blue graph and I rotate it diagonally along that line where y is equal to x, if I rotate it with that as my axis of rotation, will it match up to the red graph? The answer is no, it doesn't, right? So think about what this blue graph is going to do. This part that's above the diagonal line rotates and will end up underneath it like this. And this part that's below the diagonal line will rotate above it and look something like this. This is kind of a bad drawing, but you get the idea. It doesn't match up to that graph there. So C is not correct. Now that I've kind of discussed it, I think it becomes clear which graph is the correct answer, and that's A. Right? Because that actually matches up perfectly, right? So if I draw this diagonal line where y is equal to x, and I take the blue graph and rotate it 180 degrees about that line, it'll exactly match up to the red graph. And so A is the correct answer here. It's the only answer that shows two graphs that are inverses of each other. All right, and this one's just a yes or no question. Are these two graphs inverses of each other, yes or no? And they've even helpfully drawn in this line for you where y is equal to x. So all you have to do to check is to take one of the graphs and imagine what would happen if you rotated about this diagonal line, and will it match up to the second graph? And the answer is yes. All right, so if I take this graph here and I rotate it 180 degrees about this line here, it'll exactly match up to the second graph. So the answer is yes. Another way you could check is by looking at points. I don't know if I can tell. This one looks like it's at -3, 0. If I could write a 3, right? And what should happen for the inverse, so another way to check is, so this is F. For G, for the inverse, let me just say this, for the inverse, it should be the same points but flipped around. The y coordinate should become the x coordinate should become the y coordinate. So the inverse function should have this point on it. And it does, right? It has this point right here. So when I rotate it around this diagonal line, this point ends up here. Right? And so we could check other points as well. So another way to tell if two graphs are inverses is look at points on one graph, flip the x and y coordinates around, and see if those points show up on the other graph. If they do, then the graphs appear to be inverses of each other. All right, so I'm going to go ahead and stop there. That concludes my video on section 2.5. I will see you in the next video, section 2.6.